So, welcome to the 7th lecture about computer science, and in this lecture I would like to talk about two things, and one of them will be number systems, and this is also the basis for the second thing which I'm going to talk about, which is basically an introduction both to high-level programming and to assembly language, and showing the differences of the two of them. The reason why I start with number systems is that, well, maybe it is a bit easier to understand how assembler works if you know a bit about number systems. Usually the number system that is used in the Western world, and more or less the other countries as well, is the decimal number systems. So this is about the number 10. Deca is Greek for 10. And this means that one digit can be from 0 to 9. So it can have 10 different and then the next digit, if you count from right to left, actually has the value multiplied by 10. And this principle is actually the principle that is used in all of these number systems, but except the Latin number system, for example, which is a bit different and irrelevant actually for computer science. But in computer science, sometimes there are basically two other numerical systems, number systems, that are relevant. And one of them is the hexadecimal system, and the other is the binary or dual system. So actually, sorry, the the hexadecimal system, or also called C-decimal system, this is a number system with the base 16. Instead of 10, we have 16. So, because our culture is used to the decimal system, we only have the digits 0 to 9, but in the hexadecimal system, there should actually be 16 digits, and this is the reason why after 9 comes A, then B, C, D, E. So, and eventually F. So, F, for example, would correspond to the number 15. So 9 plus 6 is 15. That's why we have A through F as additional digits. And the other things are similar to the decimal system. So if we write a digit a bit left to the others, this is a multiplication with 16. So this means that, for example, if we have a number 100, and this is an hexadecimal number, this is not 100, but this is 1 times 16 times 16. So it is 256. And actually there is one reason why this hexadecimal system is often used in computer science and in computer programming, and this is that 16 is a power of 2. And usually computers work with registers that have a size of 1 byte, 2 bytes, 4 bytes, 8 bytes, and so on. And a byte itself can take up to 256 different values. So 256 values can be represented by 2 hexadecimal digits. I already explained why. Because 100 would be 256. So FF would be 255. And when we have values ranging from 0 to 255, these are 256 values. So we can easily represent a byte by 2 hexadecimal digits. And so if we have a register with 4 bytes, then actually, or let's start with 2 bytes, then it would be 4 hexadecimal digits. And this is relevant for assembler programming because you have such registers which are 1 byte or 2 bytes or 4 bytes and so on. And you can usually subdivide these registers. So for example, you can have a register, let's call it AX, which is 4 hexadecimal digits. And this can be subdivided into AH and AL. AH being 2 hexadecimal digits and AL being 2 hexadecimal digits as well. If you assign a value to AX, then you can easily see, if you do it in a hexadecimal way, which value gets assigned to AH and which gets assigned to AL. And the other system which I mentioned was the binary system or dual system. So this is very simple. You only have the digits 0 and 1. And instead of multiplying with 10 or multiplying with 16, you multiply with 2. This is actually not often used, but it does actually have a usage because also in assembler, you often manipulate registers which are supposed to contain flags. And flags are usually just values of 0 or 1. And these 0 and 1, these are also called Boolean values because you can easily use them for Boolean algebra, which is a way of logic, mathematical logic. You can assign the truth value false to 0 and true to 1. And so it is usually that a register has flags, and if one flag is equal to 1, then the flag is set, and if it is equal to 0, it is unset. Setting flags actually can be done by using disjunction, logical disjunction, because if you have a parameter which is the current state of the flag register, and then you make a disjunction, an OR operation with a value that is actually a power of 2. Then, depending on what power of 2 this is, a particular bit, so to speak, so a binary digit of this register can be set. Because if you have any value and make a disjunction with true, then the result is true. So you can set this flag in this way. You just have to know at which position the flag is located, and you have to use bit shifts. So bit shift means you set a variable to 1, and if you shift it, for example, by 8, then it becomes 2 to the power of 8. And in a similar fashion, you can also unset flags. But it is, of course, with a conjunction. The conjunction means that the single bit which you want to have unset must be 0 in the parameter which is used for the unsetting, while all other bits have to be 1, because if they are 1, then this doesn't change in conjunction, because both false and true in conjunction with true remain unaltered, but conjunction with false makes the result false. So usually in this case you create the mask by also doing the bit shift trick, the same way with the disjunction, but then you negate this parameter. So you turn around all the bits in the value, and then you do the conjunction. And the reason why I told you about this is that this is quite relevant to assembly language. Assembly language being a programming language that comes close to machine language, but machine language is the language which the computer internally uses to process computer programs. However, it is very difficult to read machine language for a human. So assembly language was developed, which is very close to machine language, but is somewhat readable for humans. It is a complete programming language. You can write any program you want with assembly language, but compared to a higher level programming language, it's simply much more work, because you don't have for loops, you don't have while loops, you don't even have if conditionals. Basically, you just enter instructions that can be processed by the machine. So actually, nowadays it is hardly ever used, not even in size-limited programs, but sometimes it was used in the days of MS-DOS for certain program routines, which are very important because they have to be either very small or very fast. And both things are possible with assembly. You can create very small programs and you can create very fast programs. Depending on what is more important to you, you have to decide whether you optimize for size or for speed. But nowadays, higher level languages are often used simply because the computers are so fast, and also the compilers which generate the machine code are usually quite sophisticated and optimize the code. So it is not just a translation to machine code, but the compilers also take a look at how this machine code can be transformed so that it is pretty small and pretty fast. So this is called optimization. And programming in a high-level programming language is simply easier. It is also easier to understand programs written in this higher-level language, and that's why this is regularly done. So most higher-level languages nowadays are based on C. They have a similar syntax as C, so the commands which we regularly use are more or less the same in all these programming languages. The differences mainly concern details. But if you know C or C++ or C# or Java, if you know one of them, you are basically able to program in all of these programming languages. So a C program usually has at least a main function, which is the function which the computer executes when the computer starts running the program. Usually it's called main, written in lowercase letters, but in Windows, for example, it is called winmain, and it can also have other names. This depends mainly on the compiler settings. So this function main is called and the instructions are processed. And of course the instructions themselves can again be called to other functions, which can in turn call other functions, and so on. And that's why these programs can be very complex. So the difference to old programming languages such as BASIC is that in BASIC you didn't have functions, so you had just one program that was processed from the top to the bottom, or at least until some sort of code suggesting that the program should be terminated was executed, or maybe the program would never terminate because it ended up in an endless loop. This could also happen. So in C you have this main function, and as said, nowadays most professional programmers use object-oriented programming, so you actually have objects. So you don't just have functions, you have objects. Actually these objects are instances of classes. So you actually define the classes and then you create objects from these classes. So I actually already talked about higher level programming languages in the previous lectures. So this was mainly to introduce you to assembly programming. And what I still want to say is that basically an assembler program, when you start an executable file, the executable file is loaded into the memory of the computer. So the memory is something where both data and code can be stored. It is basically the von Neumann architecture. Von Neumann, this was an Hungarian mathematician who invented the architecture how computers work nowadays. In the von Neumann architecture, there is only one memory in which both code and data are stored. So all pieces of data can be interpreted as code, and all pieces of code can be interpreted as data. There's not a strict separation. But it depends, of course, where the instruction pointer points to, whether something is executed as code or as data. So the instruction pointer points to the instruction which the central processing unit of the computer is supposed to execute next. Well, it's as simple as that. The instruction pointer is automatically incremented after the instruction, usually to go to the next command. The command is basically a value that is interpreted by the machine and tells what the machine should do. If it is a jump command, then of course the instruction pointer changes its value. And then we arrive at a different part of the program. So then it is not linear anymore. So in MS-DOS actually we used to have either programs that had one segment or several segments, a segment being a space of 64 kilobytes, and you could define a code segment and a data segment, with the code segment storing the instructions in the data segment storing the data, which had to be processed. But as said, there were also programs which had only one segment, so there was no strict separation of call and data, and so you could, for example, also overwrite code, and so you could create self-modifying executables, and this is something which virus programmers often did. So polymorphic viruses were based on this principle. So much could be said about assembly language, but I think for now I will stop talking, and I hope you enjoyed this, and if there is something you didn't understand, then well, watch this again, and see you.